To understand errors, we first need to understand the happy path. What happens when everything goes right? The secret lies with the call stack. Imagine it as a meticulous manager's to-do list, specifically for functions. It follows a simple but powerful rule: last in, first out, or LIFO. The last task, or function, added is the very first one to be completed and removed. This structure is the backbone of your program's execution flow.
So what gets placed onto this stack? Every time a function is called, a package of information called a stack frame is created and pushed onto the top. This frame is crucial. It contains everything that function needs to do its job and return correctly, including its local variables, arguments passed to it, and, most importantly, the return address, the exact spot in the code it needs to go back to when it's finished.
Let's visualize this process. When your program starts, the main execution context, let's call it main, is pushed onto the stack. If main calls a function named dataGeta, a new stack frame for dataGeta is pushed on top. Then, if dataGeta calls another function, parseData, its frame is pushed on top of dataGeta. At this moment, the stack gives us a perfect snapshot of the current execution path. parseData is running, was called by dataGeta, which was called by main. Following the LIFO principle, once parseData finishes its job successfully, its stack frame is popped off the stack. Control returns to getData, right where it left off. When getData completes, its frame is popped, and control returns to main. Finally, main finishes, its frame is popped, and the stack is empty. This is the ideal error-free execution flow, where every function completes its task and cleans up after itself. But our happy path has a dark side. What happens if parseData encounters a situation it can't handle? For instance, it tries to read a property from null or divide by zero. At this moment, an error is created, or thrown. The normal flow of execution stops dead in its tracks. The function can no longer complete its task and pop off the stack gracefully. It's now in a critical error state. Now that parseData has thrown an error, the program asks a crucial question. Is there any code within parseData designed to catch this specific error? If the answer is no, the error can't stay there. It begins a process called propagation, or bubbling up. The runtime environment concludes that parseData cannot resolve the issue, so it pops its frame off the stack and passes the error down to the function that called it, getData. This process of popping frames off the stack in search of a handler is called stack unwinding. The runtime is now checking data.js. Does it have code to handle this error? If not, the same thing happens again. Data.js's frame is unwound from the stack, and the error is passed to main. This continues all the way up the stack. If the error reaches the very top, the global scope, and still no handler is found, the program has no choice. It crashes. To prevent this catastrophic crash, we need a safety net. In most modern languages, this safety net is the try-catch block. The try block is where you place your risky code, the operations that might throw an error. The catch block is the designated error handler. If an error occurs inside try, the normal execution is diverted immediately to the catch block, and the crash is averted. The catch block is given the error object as an argument, so you can inspect what went wrong. Let's add another crucial piece, the finally block. This block is special because its code runs regardless of whether an error occurred or not. It executes after the try block if it was successful, or after the catch block if an error was handled. This makes it the perfect place for cleanup operations, like closing a file, disconnecting from a database, or releasing a network resource, ensuring these critical actions always happen. Now, let's apply this. Imagine our parseData function now wraps its risky code in a try-catch block. When the error occurs, it's immediately caught by the catch block within parseData. The error propagation stops right there. The function can log the error, return a default value, and then complete its execution normally. The stack unwinding never even starts, and getData remains completely unaware that a problem ever happened. Alternatively, parseData might not be the right place to handle the error. Perhaps only getData knows how to recover. In this case, parseData would have no try-catch. The error propagates up to getData, which has its call to parseData wrapped in a try-catch block. The error is caught one level up. This allows for more contextual error handling, where the calling function decides the appropriate course of action. When an error is caught, you get an error object. This object's most valuable property is the stack trace. Think of it as a detailed incident report or a flight recorder for your code. It's a string of text that shows the exact sequence of function calls, the state of the call stack, at the moment the error was thrown. It's the single most important tool you have for debugging why and where something went wrong. Let's learn how to read it. A stack trace is read from top to bottom. The very top line tells you about the error itself and where it occurred. This is the scene of the crime. Each subsequent line represents one step back up the call stack, showing which function called the one above it, in which file, and at what line number. The trace ends with the initial call that started the entire sequence. By reading it, you can trace the execution path that led directly to the failure. Not all errors are the same. It's useful to categorize them. Programmer errors are bugs in the code, a null reference, an incorrect algorithm. These are things you should fix. Operational errors, on the other hand, are runtime problems from external systems. A network connection failed, a file is missing, the database is down. These aren't bugs, but they are situations your application must anticipate and handle gracefully, perhaps by retrying or informing the user. For handling specific operational errors, generic error types are often not enough. This is where you can create custom errors. By defining your own error classes, like network error or validation error, you can make your error handling logic far more precise. Your catch block can then check the type of error it received and react differently to a validation problem versus a database failure, leading to cleaner and more maintainable code. Sometimes, a function can handle part of an error, like logging it, but can't fully resolve it. In this scenario, it can rethrow the error. After performing its action in the catch block, it uses the throw keyword again to send the original error or a new, more specific custom error further up the stack. This allows for layered error handling, where different levels of the stack can contribute to managing a single problem without stopping its propagation entirely. As applications grow, placing try-catch blocks everywhere becomes messy. A superior strategy is centralized error handling. This involves creating a single, dedicated module or middleware whose job is to catch all errors from a specific application layer, like your API routes. This central handler can then ensure all errors are logged consistently, formatted correctly for the user, and trigger alerts, providing a single point of control and simplifying your business logic. What about the errors that nobody catches? For these, we have a final safety net, a global unhandled exception handler. This is a top-level listener that you register with your application's runtime. It gets triggered only when an error has propagated all the way up the stack without being caught. While it can't always prevent a crash, it's your last chance to log the fatal error, perform emergency cleanup, and display a polite message to the user before the application terminates. Let's summarize with some golden rules. First, be specific. Catch errors you can actually handle and let others propagate. Second, log effectively. Always include the stack trace and context. Third, never fail silently. A suppressed error is a ticking time bomb. And finally, provide clear feedback. Inform the user gracefully without exposing sensitive system details. Following these practices is the hallmark of a professional, resilient application.
Today, we've journeyed from the normal execution flow of the call stack to the chaos of an unhandled exception, and finally, to the control offered by strategic error handling. You've learned how to catch, analyze, and manage errors at every level. Remember, great error handling isn't about avoiding failure. It's about building systems that anticipate it, learn from it, and survive it. You are now equipped to build truly resilient software. Happy coding!